Hello again. This is Math 1120 and Math 1220 coming to you from the College of DuPage. The title of this lecture is Additional Material Concerning Linear Regression Analysis. As always, please be attentive learners while watching this video. In previous videos and lectures, we've talked about scatter plots, which were graphical displays of X and Y data. We talked about correlation coefficients, the Pearson correlation coefficient, which helps us determine how much like a linear relationship is something. And we also talked about ways to come up with an equation for this line called a least squares regression line. We enhanced that with some additional material where we talk about the question of, is a line good enough to use? And this will involve the Table 2 test. And we will also talk about using Excel to find the slope and the intercept for the least squares regression line. Finally, in this video, we will talk about the amount of variation that is explained by the regression line itself. Let's begin with a discussion of the question of, is a line good enough to use? And this is Table 2 test. So a question you may have been asking yourself is, how do I know the correlation between two variables is strong enough for me to conclude that a linear relationship exists between them? Although rigorous tests can answer this question, for now we'll be content with a simple comparison test. And again, the question is if a linear relation exists or not. If a linear relationship does exist, it is good enough to use. So to test this, there are 3 steps. Determine the absolute value of the correlation coefficient. And you remember that the absolute value of 5 was 5, the absolute value of -4 is 4, and the absolute value of 0 is 0. Basically, you drop the SIGN, it is always non-negative. So first step, you determine the absolute value of the correlation coefficient, which could be negative or positive. Step 2, find the critical value in Table 2 from Appendix A for the given sample size. We will show you this Table 2 in just a moment. And step 3, if the absolute value of the correlation coefficient is greater than the critical value, then a linear relationship exists, meaning it's good enough to use between the two variables. Otherwise, no linear relationship exists. Another way to look at the procedure is to consider this figure shown here. If the correlation coefficient is positive and greater than the critical value, here's the critical value, then there is a positive association. And the variables are positively associated, positively correlated. It's a positive slope. If the correlation coefficient is negative and less than the opposite of the critical value, here's the negative critical value, the variables are negatively associated. That means there's a negative slope, and the line again is good enough to use. This is what Table 2 looks like. In this column you have N, which is the sample size, and you see you go from a sample size of 3 all the way down to 30. Sample sizes of 1 and 2 don't make any sense because through one point you could have an infinite number of lines, and through 2 points there's only one line. But here you're finding the line of best fit. So this is the sample size, and this is the correlation coefficient that you get through the calculations that we've talked about. Again, testing for the linear relationship, you determine the absolute value of the correlation coefficient that you have. Find the critical value from Appendix A for the given sample size. So you look at the sample size and find the critical value. These are the critical values. If the absolute value of the correlation coefficient in your data is greater than the critical value, then a linear relation exists between the two variables. Otherwise, no linear relation exists. Let's look at an example. So we're going to use this data about club speed and distance, and we're going to determine whether a linear relationship exists between club head speed and distance. Well, we'll either use the Pearson correlation coefficient, which is shown as Pearson, or also the same thing is included in Excel called correlation. And so you click on the FX and you get this, and you fill in the data, and that we're going to have data that is considering the association between the club head speed and the distance. So we pull those down and we do the calculation, and we get that the value is 0.938 and change. So we follow the step then, so we calculate that, and we get that this is 0.939 when we round that off to 3 digits after the decimal place. Now table 2, we look, and there are 8 data points here. So go down to n equal 8, and we see that the critical value is 0.707. So the critical value is 0.707 because the absolute value of 0.939 equals 0.939 is greater than 0.707. A positive association exists between, and that means the line is good enough to use. Let's move on to the next topic, which is building upon the video you watched about least squares regression line, finding the coefficients using our equations, but then using Excel, which can be faster and you will be allowed to use. Just reminding you again, the least squares regression line is the line that minimizes the sum of the squared errors or residuals. This line minimizes the sum of the squared vertical distances between the observed values of y and those predicted by the line, often called y hat. And we represent this as minimize the summation of the residuals squared. Now in the video you learned formulas for these. And so the equation is going to be y hat equals, this is the slope called b1x plus b0. That's the slope. This is the y-intercept, where b1, which is the slope, is going to be the correlation coefficient times the sample standard deviation of the response variable y divided by the standard deviation of the explanatory variable x. That's the slope. That's actually quite a calculation because these calculations are involved. And b0 can be found with this equation equal y bar, which is the average of the y's, minus b1, which is the number you had here, times x bar. And that's the y-intercept of the least squared regression line. There are other formulas that you can use for B1, such as this one. As you can see, there's quite a bit involved, and you would be encouraged to use Excel rather than try to calculate this by hand. And this tells you what those things were. I already did that. Okay, so finding it by hand, then, if we look at this data where these are the values of x and these are the values of y, these are the calculations that would happen, and in fact the Excel spreadsheet would probably be much longer than this, and we would then have to divide by n-1. And so when we do this calculation, you may want to try this calculation, you get minus 0.946. So that is the value that we get for R, the correlation coefficient. You can see that's here. Now x bar is 4, s sub x is 2.44 and change, and sy is 5.61 and change. You substitute those into the formulas that I showed you previously. This one, you substitute those numbers in, this is what you get, and you substitute the other numbers in, do this calculation, you get this. So the least squares regression line for this data is y hat is equal to the slope minus 21676x plus 18.6704. So you can do all of this calculation, or you can use Excel. Let's talk about using Excel. So here's your data entered in. And what you do is you make note that you're putting the slope there, but then you click on this button, and this button brings up a dialog box and puts the equal sign in there for you. And then we scroll down to find something that is called slope, and notice that it tells you what it is. This slope, if you input the known y's and the known x's in that order, this will return the slope of the linear regression line through the given points. So what you're going to do is click OK. And then you will take the y's first, these values, b2 through b6, and then the known x's, a2 through a6. It does a calculation, and notice it gives us the same answer that we had before, minus 216 with the 6 repeating. And this is the formula if you were just to type it in straight away. So there's the answer, and if you want to have that display in this cell like we did, you'll click OK, and it will be there like this for you to use again. Similarly, what you can do is we have the data, and you can click F sub x, and you can hunt for intercept. And here's intercept of the known y's and the known x's. Now this calculates the point at which the line will intersect the y-axis by using the best fit line. So that's what we want to do. So we click OK, and we've created a spot to have this appear as well. And now we click OK. And we then pull down and we put the known y's, and then we pull down, put the known x's. It does a calculation. You see we get 18.6 and change, keeps going. The 6 is always repeating. And if I hit OK, it will populate this field so I can use that number again, which often you would want to use again. Okay, so we've talked about this, and we've talked about this. The last topic is we want to talk about the amount of variation that is explained by the regression line. And this is determined by what we call the coefficient of determination. It is denoted by capital R squared. And this measures the proportion of the total variation in the response variable that is explained by the least squares regression line. In other words, the coefficient of determination is a measure of how well the least squares regression line describes the relation between the explanatory and response variables. The closer R squared is to 1, the better the line describes how the changes in the explanatory variable affect the value of the response variable. So for linear regression analysis, we find that capital R squared is equal to lowercase r squared, a very easy calculation. Note that this is not true for multilinear regression, but we're not studying that in this course. Again, R squared is the ratio of the explained variation by the regression line divided by the total variation seen in the data. Let's talk about a problem. Determine and interpret the coefficient of determination R squared for the clubhead speed versus distance data shown in this table. And here it is repeated again. So we get these X and Y's. Now previously we computed this and found that R was 0.939, so capital R squared is that squared. And when you square a number less than 1, you get a smaller number yet. And so this is 88.2%. What this means is that the variation in distance that is explained by the least squares regression line is 88.2% of the total variation. And 11.8% of the variation in distance is explained by other factors. A very valuable thing to know about. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and each other. We're all in this together. May God bless you all.